Now I'd like to call up Dr. Urban Cleve from Germany, who's going to be speaking on breeding of fissile Uranium-233 by the use of Thorium-232 with Pebble fuel elements in a THTR reactor. So let's welcome Dr. Urban Cleve.
Thank you very much.
Dear ladies and gentlemen, I would like to thank Mr. LaRouche and his wife to be able to speak at this conference. I have two novelties for you. I am speaking in German because I'm more able to do it than in English. And second, I've made a view back into the past, not the future. But I would like to My speech will be about the breeding of fissile Uranium-233 by use of Thorium-232 with Pebble fuel elements in a Thorium reactor power station. On September 29, 2010, I gave a speech at an EIR event in Frankfurt with the theme Technology and Future Possibility Applications of Nuclear High-Temperature Reactors. This reactor was developed in Germany. It has worked for 22 years without any problems.
Entschuldigung, ich hoffe, das geht jetzt besser. Der AVR-Reaktor ist also 22 Jahre gelaufen.
This reactor ran for 22 years with there was 2.4 million fuel rods were used during that time. I said in a speech 2 years ago, the use of thorium, Thorium-232 allows the breeding of fissile Uranium-233 as a new fuel. Therefore, the reserves of U-235 in combination with Thorium-232 will suffice indefinitely. I'm glad I can speak today. Professor Schulten said 30 years ago, he spoke about this technology in a similar forum 30 years ago. I'm unfortunately the only living man who works in that team of BBC Krupp. And when I see the young people here, I feel younger. So what is thorium? It can be found in small amounts in the Earth's crust. It accumulates, among other places, as a non-usable waste product of the quarrying of rare earths. It is a silver crystal, but often oxidizes and becomes grayish-black. It is considered a radioactive element. Melting point is 1,842 degrees. From Thorium-232 with neutrons, which are better suited than fast neutrons, breeds thorium protactinium-233. And then it becomes Uranium-233. It can be used as fertile material in thermal reactors such as THTR and the AVR, and also the Chinese development HTR-10 use.
Und HTR-PB, das ist der neueste Reaktor, der zurzeit im Bau ist, mit einer Leistung von 200 Megawatt Elektrik.
The newest reactor building now is 220 megawatt. You see it in and the one in the middle is 300 megawatt electric. The German development of this technology was already tested, at the time the only one in the world. Now, more than 20 years later, this technology is accorded great significance worldwide, particularly in China, but also in Japan, USA, Russia, Canada, Great Britain, France, India, South Africa, and Norway. Unfortunately, not in Germany. I will try all my life that this will be reached again in Germany. Please allow me to read a few translated excerpts from a report by Ambrose Evans Pritchard on a website by Lars Schall from January. The Chinese are running away with thorium energy, sharpening a global race for a price of clean, cheap, and safe nuclear power. In Europe, meanwhile, when it comes to thorium, we're threatened with the lights going out. And people are beginning to realize that uranium isn't sustainable. We are going to have to breed new nuclear fuel. The aim is to break free of the archaic pressured water reactors fueled by uranium, originally designed for US submarines in the 1950s, opting instead for a new generation of thorium reactors that produce far less toxic waste and cannot blow their top like Fukushima. China has enough thorium to power its electricity needs for 20,000 years. The beauty of thorium is that you cannot have a Fukushima disaster. Thorium has its flaws. It is fertile but not fissile and has to be converted into uranium-233. It can even burn up existing stockpiles of plutonium and hazardous waste. You can. These are just a few quotes from the article by Evans Pritchard from this year. These were already the basic ideas of Professor Dr. Rudolf Schulten about the development of the THTR 300 back in 1966. So he was 50 years ahead of the rest of the world in his thoughts about power engineering, and these thoughts were, and still are, a milestone in the development of nuclear power. His forward-looking ideas can really only be compared with those of Wernher von Braun about space travel. So the time has come to put his legacy into action. The German Thorium high-temperature reactor was designed and built. I show it in the picture. It's near Hamm. This reactor was designed and built in 1966 and put into operation in 1986 at the Schmeehausen power plant. It was shut down in 1989. Thus, Germany just had a more than 20-year head start in developing this technology, which the world now views as outstanding. China is building upon it with technology from Jülich. An experimental reactor with 10 megawatt is in operation, and a 2 times 250 megawatt double block reactor is under construction. So these are exactly the same elements we had in Jülich. It will probably be ready 2015. And the picture you see is 1986. It was by order of the government, was only 3 years later was shut down. Now I'm looking for the right picture. This is the Pebble bed element. A spherical fuel element with a diameter of 60 millimeter has a 5 millimeter thick graphite shell. Inside it, there are circa 15,000 to 35,000 coated particles with a diameter of 0.9 millimeter pressed into the interior of the graphite sphere. The particles contain the fuel of various compositions. Each particle thus has its own threefold containment against the escape of fission products. This element up to 35,000 of these small coated particles. This is der Grund. These particles are the reason for the extremely low radioactive load of the entire volume of the primary gas helium, with 1 × 10
Aktivität enthalten. Im Umkreis des THTR
within a 2,000-meter radius of a THTR, a total emission of the primary gas would have led to soil contamination of approximately 37,000 becquerel meter power 2 square meter if all the fallout occurred in this close range. This result can be compared to the global fallout from the Chernobyl disaster, which measured 50,000 becquerel per square meter in far-off Schmeehausen in Germany. This high safety standard is further enhanced by the barriers. These are the little spheres, the particles. This is the reactor. The core is 3 meters diameter. Around the core are graphite elements. The helium goes through this cycle. In the AVR, we had temperatures of 950 degrees. One could go even higher. It would be no problem for the materials. Now this is the core of the HTR 300 in 1966, the original design. The thick concrete walls, 4 to 6 meters. There were no airplane of the world would go through that. It's totally safe against that. And even if all the fallout would come, it would be much less dangerous than in Chernobyl, for example. In this reactor, we had twice the super GAU. Well, I think the word is wrong. GAU is enough, in my opinion. We had tests twice of this GAU, stopped all safety installations, had a fast cut-off, and in principle this was even more critical than what happened in Fukushima, and the result? At 850 degrees Celsius, we had a total stop, took out all the safety installations, and you saw that immediately the temperature of the gas went down. A few temperatures went up a little bit in the graphite. This experiment was done twice, and in 2006 it was similarly done in the Chinese HTR. This is a clear proof that the HTR is inherently safe, and we also need for the fuel elements no special procedures. As we heard, they have these problems in Japan recently. So if the cooling stops in a HTR, nothing happens. And after a few days, it can work again like before. Among the fuel compositions tested in the AVR and used in a THTR 300, with U-235, Thorium 232 and the Uranium 233, bred from that were uranium thorium C2, uranium thorium O2, UO2, THO2. There were also tests in South Africa. All the tests showed that a common combustion of these substances is possible. This makes it possible to meet the requirements of the Non-Proliferation Treaty. The Pebble fuel element is therefore the most universal, safest, and operationally simplest fuel used by any known nuclear power plants. Fuel cooling installations are not necessary. The spent fuel elements do not require refrigeration, neither in the nuclear power plant itself, nor even in storage containers. In the absence of cooling, explosions in the spent fuel holding basins, such in Fukushima, are excluded. This also eliminates all the political problems of the search for a permanent waste repository. All material can be stored safely at the site. There was a debate a short while ago about some transport of elements, but you can stand in front of these elements for hours without anything happening. And I wrote a letter to the Frau Kraft of North Rhine-Westphalia, and I would be a volunteer to sit during the transport, so-called castor containers, which is something really different. That I would be volunteer to sit there all the time during the transport, and to work that there would be no problems with the population. And it would have been good if she would have gave me a few sweets to give out to the population. So, unfortunately, this was history. In about 2-3 years ago, I was asked by Minister of Chavan to talk about the experience with the AVR. I didn't get any money for it, but it was a lot of fun for me. This was my speech about thorium. I could also show more pictures from a previous speech.
So you can take the fuel elements and carry them in your pocket. They are put into the core, and over time they drop down and are taken out once they're spent at the lower end and taken out. And they've built a installation where they could have stored several thousand fuel elements, and they managed to seal the system, and they made a lot of efforts, but over 22 years, about 10 elements per year were destroyed through the process. So this is a very, very low rate of failures. So this is the picture, what happened when they just shut off the system without any cooling system, and it took a few days, and then the whole thing was cold. And he said he had the honor to run this experiment, and while the whole thing was going, they actually could stand outside the reactor and watch, and they were prepared to do if anything happened, but it didn't happen anything. The only problem with the test was that nobody took note of it, not the media, of course. So this is, again, the different combinations of nuclear fuel that they were using in the... And there were never any radiation accidents during 21 years of operation. Most important thing was the concrete cast instead of steel. The concrete cannot explode. They constructed it for 40 atmosphere pressure, and they put this under a pressure of 200 atmospheres. And several of the cables that keep that are within the concrete.
Ich soll jetzt schnell machen. Wie viel Zeit habe ich noch, wenn ich so lange rede wie die anderen? Aber ich mache Schluss. Ich gucke mal durch, ob da noch etwas ist.
He's coming to an end. He just looks through if there's one other. So there is no, the concrete cast will not break. It's not possible. Okay. Hope I could give you some information about what in nuclear technology was developed in Germany 20 years ago. And I'm not without hope that we can recover this and rebuild. And I hope for myself, and I wish for you, that this happened, because Germany was leading the world in nuclear technology 20 years ago. And it's a pity that all that money that had been spent for the development of nuclear energy is getting wasted, because just because it's called nuclear power reactor and it's all lumped together with all kinds of different constructions where there might arise